So, vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. We're going to talk about those. The vapor pressure, there's no calculation that's necessary for that one. We're just going to talk about it. These other three, there is a formula that will be given to you on your formula sheet. You just need to know how to put the numbers in. Okay? So the formulas are given to you. You just need to know what numbers to use in the formula and where. These two, the formula is very simple. Okay? So, vapor pressure is essentially, you have a liquid and it will evaporate. It will evaporate until there is a pressure of that liquid exerted back down on it. And that's called the vapor pressure. The pressure that's keeping it back. So if I have an empty container, I put water in it, and then I put a lid on it, the water will evaporate inside of that container until the water pressure above it equilibrates with the evaporation of the water. And so it's evaporating, condensing at the exact same rate. It's reached an equilibrium. There's no change in the water level. But if I remove the lid, the water will just continue to evaporate because there's no pressure being exerted back on it. And so that's the vapor pressure. So water has a specific vapor pressure. Ethanol has another vapor pressure. Okay? And those vapor pressures are determined by their polarities and things. But then also, if you dissolve something into that solution, it's going to change the vapor pressure. It will lower the vapor pressure if you dissolve something into the solution. And it has to do with Raoult's law. Here's the pure substance. Here's the other thing. So the other thing, because something's dissolved into that pure substance, it's kind of holding those particles in place and not allowing them to evaporate as easily. So they cannot escape as easily. And so you lower the vapor pressure. Okay? And that's what Raoult's law is trying to help us understand. Okay, now, freezing point depression and boiling point elevation. So if you have a solution, or I should say a pure substance like water, it boils at a very set temperature. This is pure water, so it boils at 100 degrees Celsius. It's pure water, so it freezes at 0 degrees Celsius. Now, if I take some salt and I dissolve that salt into the water, that changes the boiling temperature, and it's called a boiling point elevation. It elevates it above 100. It now boils at a temperature hotter than 100. So the boiling point has rise. What's that? It does. And we call the freezing point temperature change freezing point depression. So that same thing that's in there will depress the freezing temperature, and it will elevate the boiling temperature. And we can calculate by how much. Okay? And that's what we're going to do with this equation. The change in the freezing temperature is equal to the freezing constant times the molality. And we haven't talked about molality yet, but that's just kind of like molarity. So just think of it right now as the molarity. And for purposes of this class, you don't have to distinguish the two. For this equation, if they give you the molarity, you can just use it. If they give you the molality, use that. Okay? It doesn't matter. It's not going to change it enough. All right? So either way, use the molarity or the molality here. Okay, so let me rewrite that so it looks a little better. Delta TF, the change in the freezing temperature is equal to the KF times the molality, or molarity, I'll say. Now, there's one thing I will add to that, times I. And what I is called the von Hoff factor. You don't have to remember that name. But it is a factor that is helping us understand the number of particles in a solution that is ionic. So, for example, sodium chloride versus glucose okay? This one is covalent. Glucose is covalent. Sodium chloride is ionic. So, how many particles does sodium chloride become when I dissolve it in water? 2. 2 particles. How many particles does this become when I dissolve it in water? 1. It stays together. It's covalent, so it doesn't break apart. So if I have a 0.5 molar solution of sodium chloride and a 0.5 molar solution of glucose, and I want to use this in my equation, then I need to multiply the sodium chloride by 2. So it's actually 1 molar. And this one stays the same, 0.5 molar. So in this equation, this I is by how much you need to multiply the molarity by. So for sodium chloride, I use a 2 there. What would be the von Hoff factor for this? How many particles does that break up into? How many? Well, I have 3 calciums, and I have 2 phosphates, 2 PO4s. PO4 stays together, it's one thing. I have 2 of those, and I have 3 calcium. So how many? 5 particles. So I here, the von Hoff factor is 5 for calcium phosphate. Okay? Because the other one was covalent. That's ionic. How do I know if it's ionic or covalent? I look at the first element. If it's a metal, it's what? It's ionic. If it's a non-metal, it's covalent. Okay? The other one was C6H12O6. Starts with carbon. That's a covalent molecule. Okay? H2O, that's a covalent molecule. It's water. Okay? So that's what you're looking at. You're looking at whether it's ionic or covalent. If it's ionic, it will break apart. This is going to break up into 5 pieces. 3 calciums, 2 phosphates, so I need to multiply my molarity by 5. If that's the compound that I was using. Okay, let's do an example. It is 1. If it's covalent, it's always together. Okay? It's always 1. So the KF for water is 1.84 degrees Celsius per molal. Okay? That is a given thing, and you will always be given that. You don't have to memorize that. It will be given to you in the question or on the reference material. Just have to find it. It's 1.84 degrees Celsius for every molal. You have a 3.6 molar solution of magnesium chloride in water. What is the freezing temp? What is the freezing temperature? Okay, so I'm going to use my equation. Delta TF, the change in the freezing temperature, is equal to the KF times the molality times I. Okay, my KF is what? 1.84 degrees Celsius per molal. What's my molality? We're just going to use molarity and molality as the same thing. 3.6 molar. What is my I? 3. 1 magnesium, 2 chlorine, so it's 3. It will. And in this case, it's ionic, right? So it's going to stay together. Okay, so what is my change in temperature? 1.84 times 3.6 times 3. Say it again. 19.872. Okay. Okay. So I haven't answered the question. What is the question? What's the freezing temperature? What did I find? The change in the freezing temperature, or the change in temperature.
So it's negative 19.
Yes, it is. The answer is minus 19.872 degrees Celsius is the freezing temperature. How do I know? Because I started at 0, right? And it changed by 19.872 degrees Celsius. It goes down by that much. So my new freezing temperature is negative 19.872 degrees Celsius.
Is that what it's in a while?
It will be for you guys. You guys only have to worry about water. But if it wasn't water, they would still give you the KF for that solution.
So the same thing with the boiling. Whatever the changes, these are added.
What would they give you the boiling and
You add it.
before, like in this new substance?
So when you freeze it, you subtract
Like
it.
if you're specifying the freezing point or boiling point of different substances.
Then they would say these are the freezing and boiling points of that
That's
substance.
difficult to do if you didn't know.
No, yeah, they would tell you that. Yeah, it would go up. So let's do a boiling. What's that? No. If you dissolve something into it, it always raises it. It doesn't ever lower the boiling point, except for pressure. That's the only thing. Okay? But something that goes into it doesn't lower it. It always raises it. So, the boiling temperature equation is the same. The change in the boiling temperature is equal to the boiling constant times the molality times I. Once again, times I. So let's do a question for this. The KB for water is 0.52 degrees Celsius per molal. The boiling constant. Water? Was freezing. This is the boiling constant. The freezing constant is different than the boiling constant. Okay? So this is the Kb of water. The Kf of water was 1.82. The Kb of water is 0.52. You have a 2.87 molar solution of PCl3. Okay, so this is in water. You took some PCl3, you dissolved it in water. What is the new boiling temperature? So delta TB, the change in the boiling temperature is equal to the Kb times the molality times I. My Kb is 0.52 degrees Celsius per molal. Times, well, let's get there, 2.87 molar times I, and I have a 4. Does anybody else have another idea what I is? 1. It is covalent. Okay, yeah, make sure. Okay, so it's 1 because this is a covalent molecule. Potassium is a metal because that's phosphorus.
Oh, why was those? Wow. Never mind.
You're seeing P right there for Carrie. Yeah. Okay.
I saw the P up there and I thought potassium. So.
Right. Okay. Okay. So this is a covalent molecule. What is the boiling temperature? What is the change in the boiling temperature? 1 point what? So the new boiling temperature is 101.4924 degrees Celsius. So you can imagine you're going to have two answers on your test. One's going to be 1.4924. One's going to be 101.4924. Okay? You need to make sure you're choosing the right thing. If they're asking for what is the boiling temperature, you answer with this. If they're asking what is the change in the temperature, you answer with this one. Okay? So make sure you're answering the question according to what they're asking. 1.4924 degrees Celsius is how much it would change by. Okay? If it's water, water boils at 100 degrees Celsius, so it would change by that much and become 101. If it was a different substance, they would have to tell you what their boiling temperature of that substance was. But for water, they assume you know water freezes at 0 and it boils at 100. Okay? Okay. Now, they're going to define molality now. You're not really going to do a lot with this. We're not going to do molality problems, but this is what it is. Molality is equal to the moles of a solid over the kilograms of a solvent. That's different than molarity because molarity is moles per liters. This is moles per kilogram. So this is all in mass. Molarity is mass over volume. Okay? Now the reason that they actually use molality for colligative properties is because volume of something can actually change as you increase or decrease the temperature. The volume can either get larger, the density can either go up or down, okay? But for a molality, it can't change. the mass is the mass. Even if the volume gets bigger, it still weighs exactly the same, whether it's hot or cold. So that's why they use molality to determine these. But you guys aren't going to have to worry about changes in temperature or things like that. It will always be about room temperature is what they're going to give you. So you're just going to use the molarity, and that is going to be equivalent to the molality because water has a density of 1 gram per milliliter. Terrible. Okay? My pen's writing all weird. 1 gram per milliliter. Okay? So if I have 1 liter, that is equivalent to 1 kilogram. So molality and molarity in this case are essentially the same. So that's why you're just going to use it for what you guys are doing. Okay? You're not going to have to worry about changing it or anything. If they give you the molarity, use it as the molality. If they give you the molality, then use that. Okay? You don't have to convert anything. Okay, last one, osmotic pressure. Okay. I know. Okay, osmotic pressure. So what the osmotic pressure is the pressure of the water across a membrane. So there are membranes that we call semi-permeable membranes that allow for the passage of one thing but not other things. So in this case, it's the passage of water. Water can pass through the membrane, but all the other particles, like the salt particles or the glucose particles, they can't move across the membrane. It's only the water. And if the osmotic pressure is high enough on one side, it's going to push the water towards the other side until the osmotic pressures are equal. And then the water will stop moving across the membrane. So here's an example of that. Here, I have a higher salt concentration than I do over here. So water goes from high to low concentration. Water is in low concentration on this side of the membrane. It's in high concentration on this side of the membrane. So the water is going to move this way until they reach an equilibrium state. Either the salt concentrations are the same on both sides because this water is diluting this to where they are equal, or the osmotic pressure just simply stops it. So here's a pure water going this way, diluting this salty solution, and eventually it has to stop because it can't just, not every single last particle of water can go because the osmotic pressures eventually have to equilibrate across that membrane, and it will stop. This is the osmotic pressure equation. The pressure, the osmotic pressure, is equal to mRT. Does that equation look at all familiar? Well, no, that's the pi symbol. That's true. Okay, let me change that pi for an P. The pressure is equal to mRT. So what? You're not using 3.14, no. No, you're not using that number. Pi stands for the osmotic pressure. That's all. I have no idea, probably, but I don't know. It's just a Greek letter, they chose to use it there. Okay. The pressure is equal to mRT. Does it look at all familiar? Yeah? PV equals nRT. If I solve for the pressure, I'm sorry, what was that? Yes, it is. So if I solve for the pressure here, it's nRT divided by V. Or in other words, the moles divided by the liters, which is the volume. So P equals moles per liter, molarity, RT. The osmotic pressure is equal to the molarity RT. Okay? That's how they got that equation. No magical, nothing real magical, that's it. Okay? So, that's the equation. The osmotic pressure is equal to MRT, but we need to also consider I. They haven't put them on these equations, but we don't want to forget it. Okay? Because it's important to calculate the osmotic pressure equals I MRT. We can't forget about the number of particles. Sodium phosphate. How many particles?
7.
Not 7. 4. Phosphate is one thing. CO4. It's actually a covalent thing. Phosphate stays together as one thing. If I had brackets around it and I said there's 2 or 3 of them, that would change it. But there's 1 phosphate, 3 sodium. I have 4 particles. So you see, they use that for when they're calculating their molarity for this equation. Okay, so we need to include it there. 4 times the molarity times R times T. Okay, so it's a 5 times 10 to the negative third molar sodium phosphate. So I need to say 4 times 5.0 times 10 to the negative 3 times R, 0.0821 liter atmospheres. I'm going to run out of room. Kelvin. I got it from my reference sheet. Times the temperature. Did they tell me the temperature here? Well, the temperature is, they changed the question. The temperature, let's say, is 25 degrees Celsius, so that's 298 Kelvin. Why do I have to use Kelvin? Because R is in Kelvin. So I have to change this to Kelvin. I can't use Celsius here because it will not cancel. My units won't cancel between Kelvin and Celsius. So I have to use Kelvin. Okay. This is molarity, which is the moles and the liters cancel for the molarity. And I'm left with the pressure, atmospheres. Okay? Alright, so that's how we calculate that. Here's another question just like it. Calculate the osmotic pressure of a 5 times 10 to the negative 2 molar solution of sodium chloride. 5.0 times 10 to the negative 2 molar sodium chloride. It's at 25 degrees Celsius. Pi equals MRT. Okay? So, I have 5.0 times 10 to the negative 2 molar times, what's my I? Two. Sodium? It is ionic. It's ionic, so it breaks up into 2 pieces. R, 0.0821 liter atmospheres over Kelvin moles, and again 298 Kelvin. Kelvin cancel, moles and liter cancel for the molarity, and I'm left with atmospheres. Okay? So once again, I do all that and I get 2.4 atmospheres. times what? Times 2 times 0.0821. Okay? So that's how I'm going to get to that point. Okay. So cells, because of the osmotic pressure, will either shrivel or swell depending on the salt concentrations you put them into. So if I put a cell into something that I call a hypertonic salt solution, hyper meaning high, a lot of, like hyperactive, very active, hypersalt, hypertonic, lots of salt, the cell will shrivel because the concentration of salt outside of the cell is much greater than the concentration inside the cell, and the water will move out of the cell trying to dilute it. So it's going to shrivel up. Here, the water is going to move in because this is a hypotonic, low salt. Low salt outside of the cell, high salt inside of the cell. Water is going to move into the cell to try to dilute the salt in the cell. And if you can't stop the influx of water, the cell will actually end up bursting. And we call that hemolysis, when it bursts. So if I wanted to extract the DNA or the proteins out of a cell, I would stick it in a hypotonic solution. It would burst it open, and I could extract the DNA or the proteins from that cell. Unless it's a plant cell. Plant cells have these strong cell walls, and they love to take up all kinds of water. They love it. So you put them in a hypotonic solution, and they just swell up, and they don't care. Yeah, it's pretty cute, huh? Okay, so that's because of that cell wall. And so at the grocery store, they spray the fruits so that they swell up nice and big and fat, because you don't want to buy a shriveled up fruit, right? Okay. Unless it's a raisin. And then you're going to want to prenate it. Okay, isotonic. That means same salt. The salts are the same on the inside and the outside of the cell. That is an isotonic cell solution. Okay? So in an isotonic cell solution, if I put a cell in an isotonic, it's just going to stay the same. It's not going to do anything. So you go to your swimming pool. Well, let's start. You sit in the bathtub for 2 hours. What's going to happen to your fingers? They're going to get all wrinkly and pruny, right? Because what type of solution is my bath water? High salt or low salt?
High salt.
Well, I hope it's low salt. I don't know what kind of water you guys are being in. Okay? Okay, but if you use bath salt, you're not going to end up pruny. Okay? But it's hypotonic, so what are happening to the cells in your skin? They're absorbing water, and they get all pruny, right? And swollen. But if I go on a raft and I'm stuck at sea, what's going to happen to my skin? It's going to get all leathery and tight and shriveled and shrunken and cracked and gross, right? Because it's a hypertonic salt solution in the ocean. So what's the verdict? Don't get stranded at sea, guys. It's not fun. All right? No fun. Yeah, it does. Well, exactly. It pulls out the moisture because it's hypertonic. The water goes out. Now, does the same thing happen to you when you sit in your swimming pool for 2 hours, 3 hours? Do you get the same effect as this one? Yes. Yeah. Really? Yeah, you do. You guys need to check your like the same cream. You can usually go to your swimming pool for a lot longer without getting all pruny the same. Here you get really pruny. Here you don't. Why? Because what's in the water here? Chlorine. It's more of an isotonic solution. Okay? And so it's not, your cells aren't taking up or giving away as much water. What's that? I can't hear you so good.
What is the water that makes it do that?
Make it do what?
Make it turn blue.
I don't know. Maybe a pH indicator or something. Okay, here's your cucumber. You stick your cucumber into a vinegar solution, salty vinegar, high salt, and it becomes a pickle.
There's no way that's the same cucumber.
What are you talking about? Yeah. How do you think they make pickles? Yeah, I'm serious. They a vinegary, salty solution, and it shrivels it up. It shrinks it. It's the same thing. It's the same thing. Yeah. It's the same one. This is this. You guys are skeptical. You're gonna have to do it at home. What's that? Vinegar and salt. So if you want to know the recipe, look it up. If you want to know the exact concentrations of everything.